Hey everyone, so this is the solution video for Worksheet 10.4a. Here we're going to be using some of the identities discussed in this section to help us solve problems that otherwise we wouldn't be able to with skills we've learned so far. So for number one, we're told that we're going to use the sum and difference identities to find exact values of the sine and cosine function. So these are going to be instances where we're asked to find the sine and the cosine of an angle which we're normally not used to using in terms of reference angles that we've used so far. So we have to kind of redefine them in a way that we can find exact values, rather than having to go to our calculator. So in part A, we were asked to find the cosine of 75 degrees. 75 degrees is definitely not an angle we're used to using in terms of exact values for sines and cosines. So let's go ahead and redefine this particular angle. So if we think about ways we could write 75 degrees as a sum or difference of angles we're used to using, one thing we could consider is, well, 75 degrees is the same as the sum of 45 degrees plus 30 degrees. There's lots of different ways we could approach this, but using 45 and 30 has two particular advantages. One, 45 and 30 are angles that we know how to get the sine and cosine of rather easily. Two, 45 and 30 are angles in the first quadrant, so they're just easier to use sometimes. So we're going to go ahead and we're going to use this, and rather than finding the cosine of 75 degrees, we're going to think of this as finding the cosine of 45 degrees plus 30 degrees, which is the same thing. And now we're going to use the identity for the sum of two angles with the cosine. So it's in the text, should be in your notes, but the way we would do this is we're going to say, well, I'm going to let this be my alpha. I'm going to let 30 degrees be my beta. And then using the identity, we can rewrite this as the cosine of 45 degrees times the cosine of 30 degrees minus the sine of 45 degrees times the sine of 30 degrees. So now these are values that we should be able to relatively easily get the exact values for. So let's think about this. Cosine of 45 degrees. We should be pretty comfortable in saying that we know this is the square root of 2 divided by 2. Cosine of 30 degrees is going to be the square root of 3 divided by 2. The sine of 45 degrees is the square root of 2 divided by 2. And the sine of 30 degrees is positive 1/2. So we multiply these together. Square root of 2 times the square root of 3. With multiplication, we can bring those numbers inside of the radical. And then we've got over 4 minus the square root of 2 over 4. So we combine these with our common denominator, and we have the square root of 6 minus the square root of 2 all over 4. And then that would be our exact solution. So you could have picked different angles to get that 75 degrees other than 45 and 30, and you probably could have used a difference instead of a sum to get that, but this is one way that we could get there. Okay, so let's do a similar maneuver here with part B. So we're asked to find the sine of 7 pi over 12. So 7 pi over 12 is not something we either see in the unit circle or have run into with reference angles. So let's think about this. First, it might be easier to get this into degrees. It's just a little bit easier to work with. So let's consider that, well, 7 pi divided by 12, if we converted this into degrees, would give us 105 degrees. And if we wanted to think of this as sum and difference, this is the same. The 105 degrees is just 60 degrees plus 45 degrees. So what we can say now is that the sine of 7 pi divided by 12, well, first of all, it's going to be the same as just the sine of 105 degrees. More importantly, we can write this as the sine of 60 degrees plus 45 degrees. And then we'll use the sum identity for the sine, where 60 degrees represents our alpha and 45 degrees will be the beta. And the identity will have us construct the following value. So we'd have the sine of alpha times the cosine of beta plus the cosine of alpha times the sine of beta. Now in this case, order doesn't matter as much because multiplication and addition are both commutative, so it doesn't really matter that much, but it's good to kind of keep it in line with the identities just to be sure. So now we find the values of these four trig functions at the given angles. Sine of 60 is going to be the square root of 3 divided by 2. Cosine of 45 is going to be the square root of 2 divided by 2. Plus cosine of 60 is 1/2. And then the sine of 45 is root 2 divided by 2. So we'll bring this together. So square root of 3 times the square root of 2 is the square root of 6, all over 2 times 2, which is 4, plus 1 times the square root of 2, which is the square root of 2, all over 2 times 2, which is 4. Bring these two fractions together, and we get root 6 plus root 2, all over 4. And that would be our solution for this one. Okay, so again, the point here being that these are exact. You could very easily just type in sine of 7 pi over 12 in your calculator and get an estimation, but when asked to find exact values, like we were in these problems, you need to go through the process of using these identities to get there. Okay, so that's one thing that these identities are good for. Another thing, let's look at this problem. So number 2. So in this case, we're looking at two different angles, alpha and beta, and we're told that the sine of alpha is 3/5, where alpha is between 0 and pi over 2. So let's just kind of make a note to ourselves that alpha is a first quadrant angle based on that. So alpha is in the first quadrant. And then beta, the cosine of beta is 12/13, where beta is a fourth quadrant angle. So now we know that beta is an angle in the fourth quadrant. We'll see why this might be helpful a little bit. So now we're asked in this problem to find the cosine of alpha plus beta, given the information that we've got. Well, let's think about how we can actually define the cosine of alpha plus beta. Well, cosine of alpha plus beta, using the sum and difference identities, we know that this is equal to the cosine of alpha times the cosine of beta minus the sine of alpha times the sine of beta. So if we knew the sine and cosine of alpha, the sine and cosine of beta, it would just be a matter of plugging these values in and getting a solution. And the good thing is we've actually got a few of these. We have the sine of alpha. We have the cosine of beta. So what we note here is what we actually need. We need the cosine of alpha and the sine of beta. If we can get those, then we'll be in good shape. Now, as with lots of these trig problems, there's definitely more than one way to do it. So I'm just going to go ahead and do one possible way of solving this problem. We're going to look at alpha and beta and see what we can figure out here. So let's consider alpha. Well, we're going to go back to using, if we wanted to find the cosine of alpha, one way to do this would be to find the x, the y, and the r, and then define cosine as x over r for alpha. So let's see what we have so far from alpha. Given this bit of information up here, that the sine of alpha is equal to 3/5, we know that sine is y over r. So our y is going to be 3, and our r is going to be 5. So if we're looking at x, y, and r for alpha, we know that y is 3. We know that r is 5. It's just x that we don't know. And if we can get x, then we can find the cosine of alpha. So we know that r squared is equal to x squared plus y squared. So r, being 5 squared, is going to be equal to x squared plus y squared, which is 3 squared. So we're going to solve this for x. So 25 minus 9 is going to be equal to x squared. And we're going to get, what this would be, 16 is equal to x squared. We take the square root of both sides, and we get x is equal to plus or minus 4. So the question is, which one is it? Is x positive 4 or is it x negative 4? Well, this is why we want to make note of the quadrant that we're in. Since alpha is the one that we're working on here, since alpha is in the first quadrant, we know that both x and y are positive. So this is just going to be positive 4. So now we can go back up here, and we can say, well, we know that x is positive 4. So with these 3 little pieces of information, we now know what we wanted was the cosine of alpha. That cosine of alpha is going to be x divided by r. And we've got one of the 2 things that we needed. We're going to do the exact same thing now for beta, to find the sine of beta. So if we consider beta, and we want to find x, y, and r, we look at what we have. We have the cosine of beta. So we know that since cosine is x over r, our x is 12, our r is 13. So x is 12, r is 13. So now we need our y. So we set this up and we say, well, but we know that r squared is equal to x squared plus y squared. So r is 13 squared, x is 12 squared, and y is what we're after. So 169, and then we subtract 12 squared, or 144 from both sides, and that's equal to y squared. So that's going to be 25 is equal to y squared. So we take the square root of both sides, and we get y is equal to plus or minus 5. Well, which one is it? Well, beta is in the 4th quadrant. So in the 4th quadrant, we know that our x's are positive and our y's are negative. So since it's 4th quadrant, it's going to be negative 5. So we can go ahead and we can put minus 5 in for y. So with these 3 pieces of information, now we can find the sine of beta. Sine of beta is going to be y divided by r, which is 13. So with these 2 things, along with the information that we were given from the start of the problem, we can now go back and solve this. So let's go ahead and do that. So cosine of alpha plus beta. Well, the cosine of alpha we recently found out was 4/5. The cosine of beta we were given as 12 divided by 13. From that we subtract the sine of alpha, which we were given as 3/5, times the sine of beta, which we just found out was negative 5/13. All right, so then we go from here. So we multiply these together and we get 48 divided by, so we take, 5 times 13, that's going to give us 65, minus 15 divided by 65, and we get 48/65 plus 15/65, which will give us a total of what? So that'll be 63/65. So even though we don't know what alpha and beta are, we know that the cosine of the sum of those two angles is going to be 63/65. Okay, so there was a lot involved there. So a consuming problem in terms of time, and again, there's definitely other ways that you could approach this, but this is a pretty tried and true one. Okay, so for number 3, we're going to use a half-angle formulas to find the exact value of the cosine of 75 degrees. So we kind of already found the exact value of the cosine of 70 degrees in number 1a using the sum and difference. We can also find the sine and cosine of angles that we normally don't associate with exact values using the half-angle formulas, and we'll see how we can do that in a second. So let's first go ahead and define the half-angle formula for the cosine. So the half-angle formula tells us that if we want the cosine of some angle theta, which we have divided by 2, so that's the half of our angle theta, this is going to be equal to plus or minus, which we have to determine using information that we're given based on the angle, 1 plus or minus the square root of 1 plus the cosine of theta, which is that angle we were dividing by 2 on the other side of the equal sign, divided by 2. So here's where we have to be careful. We're asked to find the cosine of 75 degrees. So the 75 degrees sort of plays the role of the theta over 2 here. So one way you can think about it is, well, 75 degrees is the theta divided by 2 in this problem. It's the thing that goes right here. We're finding the cosine of 75 degrees. But within this formula, we're going to need to know what theta is. Well, if theta over 2 is equal to 75 degrees, this implies that to get theta, we'd multiply both sides by 2, and we'd get theta is equal to 150 degrees. So these are the two angles that we're going to substitute into this problem. The other thing that we're going to make note of is this angle that we're taking the cosine of in the original problem. We notice that 75 degrees is an angle in the first quadrant. Okay, so that means that the cosine of 75 degrees is going to be positive, because 75 degrees is a first quadrant angle, and the cosine is positive in the first quadrant. So when we start our problem here, we can make one decision right away. So the cosine of 75 degrees, again, we could think about this as, well, we're just finding cosine of 150 degrees divided by 2, if that helps. So this is going to be equal to plus, because of this determination that we just made here, it's going to be positive the square root of 1 plus the cosine. Now this is where most of the mistakes happen in here, is that what is the cosine of theta? Well, our theta is that 150 degrees, twice the angle we want to find the cosine of in the whole problem, and that's divided by 2. So now the only other thing we need to figure out here is, well, what is the cosine of 150 degrees? So that's going to be plus the square root of 1 plus, and the cosine of 150 degrees, let's make a note of this here so we know. So cosine of 150, unit circle, reference triangles, how you want to get there is up to you. It's going to be the negative square root of 3 divided by 2. So we plug that in to our half angle formula. So it's plus minus square root of 3 divided by 2 all over 2, which if we clean this up just a little bit, we can drop the positive sign now. It's understood. we've got 1 minus the square root of 3 divided by 2 all over 2. Now, technically this is a correct solution, but to clean it up a little bit would be a good idea, and I believe it's required for your web assigned homework. So let's see how we could maybe clean this up a little bit. I mean, it's kind of messy. We've got, 1 minus a fraction over 2 under a square root. So let's see if we can kind of clean it up a little bit. Let's start by getting a common denominator here. So in the top part of this fraction that we have here, I'm going to write this as 2 over 2 minus root 3 over 2 all over 2. And this is all under the radical sign. So this is the same as the square root. We'll combine the two fractions in the top, and we get 2 minus the square root of 3 over 2. And then this is all over 2. Well, this is the same. If we divide by 2, it's the same as multiplying by a half. So we get 2 minus the square root of 3 divided by 2. That's our numerator fraction there. And we're dividing by 2 or multiplying by 1/2. So what this now gives us is the square root of 2 minus the square root of 3 all over 4. We're almost there. Now we can take, with a fraction, if we're taking the square root of a rational expression or fraction, we can take the square root at the top. And we can also take the square root at the bottom, which makes sense here because we can simplify that square root of 4. And our final solution is going to be the square root of 2 minus the square root of 3 all over 2. That would be our answer. So this is the cosine of 75 degrees. Now what you might want to do, because this is clearly a different looking expression from what we got in 1a for the cosine of 75 degrees. I think from A, so from 1a, we got cosine of 75 degrees was equal to the square root of 6 minus the square root of 2 all over 4. Well, type these in your calculator, you're going to get the exact same estimation for these. So, something to try. Okay, so we have got one more to go. And this is number 4. So we're going to use the half angle formula to find the exact value of the sine of pi over 8. So same type of thing. Let's start by identifying the half angle formula for the sine. So half angle formula for the sine is sine of theta divided by 2 is equal to plus or minus the square root of 1 minus the cosine of theta all over 2. So let's think about pi over 8. If you want to convert to degrees and work through it that way, that's fine. I'm going to stick with radians. So the role of the theta over 2 is pi over 8 here. So that's what we're finding the sine of, pi over 8. So this implies that theta, we'd multiply both sides by 2. The theta is going to be pi over 4. So these are the two angles that we'll be plugging into this formula here. So what we get is the sine of pi over 8. So that's our theta over 2 is going to be equal to plus or minus the square root of 1 minus the cosine of theta, which is twice that angle, or pi over 4, and this is all divided by 2. We want to make sure that's all under the square root right there. Okay, so let's determine if this is going to be positive or negative or not. So since pi over 8, which in degrees is 22.5 degrees, so pi over 8 is an angle in quadrant 1. So the sine of a first quadrant angle is going to be positive. So we can at least deal with the plus sign right here. So this is going to be equal to plus the square root of 1 minus, and now how about this cosine? So the cosine of pi over 4 is going to be equal to the square root of 2 over 2. So we can go ahead and we can substitute that in 2. So 1 minus the square root of 2 over 2, and this is all over 2. Again, we've got an answer right here. This is a perfectly legitimate answer, but simplification is usually a step along the way that we have to, unfortunately, suffer through. So let's go ahead and do that, kind of like we did in number 3. So we got the square root, common denominator in the top, so we'll have 2 over 2 minus the square root of 2 over 2. This is all over 2. Yeah, get ready to hear 2 a bunch of times. So if we combine this, we're going to have 2 minus the square root of 2 all over 2. That is going to be all over 2. Dividing by 2 is the same as multiplying by a half. So that's going to give us 2 minus the square root of 2 over 2. And since we were dividing by 2 over here, we're going to multiply this by a half. And this gives us the positive square root of 2 minus the square root of 2 all over 4. Oh, so we've got something that's not a 2. Unfortunately, it's not going to last very long. So we can break this up as the square root of the top, which is 2 minus the square root of 2, and the square root of bottom, which is the square root of 4, which, in the interest of keeping 2's everywhere, our final solution will be 2 minus the square root of 2, all under radical, divided by 2. So that would be our solution right there. The square root of 2 minus the square root of 2, all over 2. Okay, so that does it for the problems in this 10.4a worksheet, and I will see you guys in the next video.